Hello everyone, welcome back to Manufactoria 2022. About to try the capstone, the final problem. I don't know. There's some I haven't solved, but this is the one the game seems to think is the hardest, so let's give it a shot. Fusion tenders. This is about, oh my god, look, this is huge. About using money or energy as currency, maybe? Specialized robots tended a vast network of lunar fusion reactors, capable of supplying all Earth's energy needs many times over. Like the food burners, though, they throttled their output as part of a complex profit-maximizing scheme. What I began to wonder could I fix them? Okay, yeah. So add the two numbers. So it doesn't have subtraction, like the old Manufactoria did. Addition is hard enough. Okay, so... how do you do addition with such poor tools? Basically, you need to have tools to increase by 1 and decrease by 1. And that's it. I've already written increase by 1. So now all we need is decrease by 1. Supposing that we had both of those things, what we would do is on the left, decrease by 1. If you fail to do so, then the answer is on the right. After you've decreased by 1, then on the right, increase by 1. Ta-da! And then go back to the beginning, right? And I don't think decrease by 1 is really any harder than increase by 1. It might be easier. Because you can work from the left end of the tape. If you get a 1, you turn it into a 0, and then you're done. If you get a 0, you erase it and keep going. Wait, that doesn't make any sense. Okay, that still has to be on the right end of the tape, not the left. Like that's not how you subtract 1. So you do have to look at the right end of the tape, basically. But it's very, very similar to adding 1. I think. Ooh, maybe not. Oh, I think it might be a lot harder than adding 1. If the digit at the end is a 1, it's easy. You turn it into a 0. Oh, it's actually not that hard. You turn it into a 0, and then you're done. If the digit at the end is already a 0, then you delete it and go back to the beginning of the tape. And say, reduce this by 1, please. Sort of carrying the -1. So let's go have a look at our addition solution again, which is here. Oh, it's so beautiful. I forgot it was so tiny. I checked on Discord, by the way, and at the time of this recording, this is the best solution, and the second best is 36. When I had 32, I was already the best, but I thought, you know what, I could squeeze that down a little bit more, make a nice little 28 addition. Or not addition, but increment. So, oh my god, it's so small, I can't see it. So when I accept here, is this correct? Why am I accepting? Because all I was supposed to do was add 1. So this should no longer be accept. It should be like go back to the beginning of the other puzzle. I don't want to do any work on that giant grid. I want to do my work here, where I can see what's going on. And it should be easy enough to implement subtract 1 in this area. So we'll just do a very similar kind of structure. And whenever there's something that should be different, I'll change it. That's maybe putting it a bit more tersely than necessary. Why was I assuming here there could be no reds? And here there can be no reds also? Oh, because this is the No? Show me the solution again. How the heck does this work? So show me, like, that. I don't know. So I read the first digit, and it was a 0. Wait, it was a 0, so I just wrote it back, which I guess is allowed, although not necessary. Then I got to my first 1. I'm looking for the last digit, right? And apparently the last digit was red. And then I got to green. I'm writing a 0 to the output. And I turned the 1 in the input into a 0. That's fine. The last digit in the input was a 1. I wrote a 1. What? How the hell does this work? I wrote this just a couple episodes ago, and I'm like, what? Alright, Alright, this is a debugging exercise today, where there's no bugs except in my brain, but I still have to step through the program. So this whole section I recognize as read the last digit. Right, this kind of 4x3 is read the final digit, copying the stuff before it. Then I write green blue, and I copy a bunch of blues only from the output. I guess there must be some reason there's never any reds in the output, right? Oh, God, I'm so smart! So, the point is, remember what we did is we put a divider in between the input and the output. And I started writing to the output. Whenever the last digit in the input was a 1, I said, well, the last digit of the output must be a 0, and then carry the 1, right? But as soon as I found a 0 at the end of the input, I just said, oh, great. Let's just concatenate the input and the output by removing the 0, the green, right? So I never actually wrote any 1s to the output area. Except this one. Which is transforming the last 0, or the first 0 I found, the rightmost 0 in the input, I turned into a 1. And then I just copied all the rest of the blues to get the input lined up to the right place so I could remove the green. Okay. Wow. I was having a smart day, I guess. So how do I subtract 1? Is there a similar trick? It seems like there must be, right? If the last digit of the input is a 1, I just turn it into 0 and concatenate the input and output, right? Or... right? Okay, so let's try that on like an input like 5 mentally in our heads here. We'll walk through it together, you and me. We look at the last digit and it's a 1. So we replace it with a 0 and concatenate it with the what's left of the input, which is i.e. 10. And you end up with 100, and that's 4. That seems cool. So we didn't even use the kind of temporary output buffering space there. A more challenging problem would be 100, i.e. 4. In that case, my plan was to turn the 0 into a 1 and write it to the output. And, of course, remove it from the input in that time, so the input is now 10. Then go back to the input and say, reduce this by 1, please. I would have 10, and I would say, oh, there's a 0 at the end. Let me write that to the output as a 1, and remove the 0 from the left. Now I have a 1. Congratulations, I can reduce a 1. I can just turn the 1 into a 0 and concatenate it with the rest of the output. And that gives us the correct answer, i.e. 3. Let's do one more double check, though, and get 1101, which is 13? Yeah, 5 plus 8. That makes sense. So we do the same thing to the end, ending up with 1, 1 at the end. And then we take the 0 from... hang on. Let me just do the whole thing from scratch. 1, 0... No. 1, 1, 0, 0 is what we're starting with. Right. Not in fact 13. Because we started with 4 before. We're adding 8 to it. We now start with 12. So we have 1, 1, 0, 0. We take the 0 off the left and put it on the right as a 1. And we're left with 1, 1, 0, space 1. Now this 0 also can't be handled, so we put it in the output area as a 1. And then remove it from the left, leaving us with 1, 1. And we want to reduce that by 1. We look at the left. It's 1, 1. It ends with a 1. Congratulations. So I replace the 1 with a 0 and concatenate the input and output, leaving me 1, 0, 1, 1, which is 8 and 3 is 11. So that does work for all inputs as an algorithm. And when I'm doing the whole concatenating the input to the output, what that means is, like, copy what I wrote to the output so far, which must be all 1s, right? Because I never would have written a 0 to the output. That's crazy. Yeah. So I don't think we can just color swap this or something, can we? No, surely not. But we can reuse a lot of it. So we write 2 zeros and we read the input until we have found a digit. You know what? Let me try just color swapping it to start with. If that digit is a 0, then we write a stamp, we write a 1 to the output, and we go back and we say decrement me by 1 again. If it's a 1, then we write a 0 to the output, and we concatenate them together. I think actually just taking this and color swapping it might be subtracting 1, which is some kind of miracle, I think. This doesn't seem right, because numbers can get, well, numbers can get shorter this way, but we're allowed a leading 0 if we want, right? So You've found that the last digit was a 0. No, this is the red area. The last digit was a red, i.e. a 1. Write it to the output as a 0, and then copy all the reds that were already in the output, right? I think this is right. So we had, I want to be able to take 1s and 0s, by the way. We had red, blue, no. I had red, blue. That was a test case we were running, right? 1, 2, 4, so this is 12, and it should, we want it to yield 11, not 13. So, oops, test, run test, pause, get me here. The tape has a little too much stuff on it, I would say. This is maybe not ideal. Yeah, okay, good. So I didn't think that this would be right. Just color swapping it. How could it be right? It's quite something, huh? There must be, like, this is wrong. I bet that's what it is. We wound up with a lot of reds that we didn't expect, and this is the kind of obvious choice. So, suppose that the input ended with blue. That's what this is all about. Then I write a green, and I put a red in the output area. And then I copy all the rest of the reds. I mean, this seems correct. But it obviously isn't. So let me just step me to here. Oh, that was too far. We want to go to here, where input ends with a... Oh! The problem is I need the acceptor up here and the continuer... The acceptor down here and the continuer up here, I think, right? So if I run to here, I look at the last digit of... Well, no, that doesn't seem right. The last... How did all these ones get there? Okay. So... I read the input, it was a red, I put it back. Wait, why are there two greens? Is that right? Yeah, separate the input from the output and to end the tape. Got it. So I see a red. I put it back at the beginning of the input. See another red. I put it back at the beginning of the input. So far, so good. Although, wait. No, this is fine. Only... no, it's not. This... looks at the input. Right, there was some special... We were treating empty tape the same as 0 here. In addition. By pretending we had seen a blue, and then we output one more blue than was strictly necessary. I see. So we can't do that here. I think. I mean, on the first pass, it should be okay to pretend we've seen a blue, shouldn't it? We would just write a blue in front. Of the output every time, maybe? The input, rather? Like, wouldn't that be okay? Oh, but we're writing 1s in front now, because I color swapped everything. That's where they're all coming from. So, is it possible, then, that I could pretend I had seen a blue in this layout as well? Blues are down here. I think it would be okay to see an imaginary blue at the beginning of the input. But I'm not sure how I would do it. Well, can I not just, I mean, I can take this entry point and put it over here, right? It hurts me a little on area. But suppose... oh, get out of here. Suppose I did that. I took this entry point. I mean, I want to just, like, horizontal mirror this. Is that possible? No, because this is wrong. I'm now looking at horizontal mirroring the entire input, which is crazy, but yeah, that doesn't work. So okay, let's just let's try doing this and see if it's correct. If it's correct, we can try making it fit better. And it should actually be not too hard to make it fit, right? Just horizontal mirror that. Oh, yeah, don't... So run this test. So we have right now 12, and we want 11 at the end. I got 21. Wait, what? Really? This got too far to the left somehow. Or no, so everything's just like totally messed up. So I copy this extra blue on, kind of for no reason. Then I copy the rest of the tape until I get to the last digit, which it turns out is blue. So remember the last digit is blue. And I write a red and copy the rest of the output, which currently is empty. And I go back. And I copy a bunch of zeros. Wait, something's wrong here. This blue is seeing a blue and then going to the red state. How did that work over here? This was the red state and it saw a blue and went up. But the blue state here, okay, something's wrong. This one's pointing the wrong way. But this one's fine? Must have horizontal mirrored something incorrectly. So this one is meant to look like that, right? Right, don't run the program, run tests. This is 12, and what I output was like just total nonsense. Trying to be too greedy about making everything fit well instead of just writing an easily understandable algorithm. That's me. So I write 2 greens. Then I write a blue just for fun. Which again, should be okay. I copy blues. If I get a red, I write a blue. Go up here. And if I read an actual blue, I take the red I was holding on to and replace it with a blue. It never goes up here? Like I'm right-clicking and it's saying you never reach this node. Well, that makes sense. I think? No, it doesn't. Obviously reaches this node. Oh, is it based on where the slider is? I don't think so. Anyway. So wait, if I just run this, it gets dumped on the floor. Which, fair enough, I guess? Oh, when I read blue, I write red, and the output should only ever be red. Did this not get... Oh, I don't need to... Okay, now we at least make it back into the loop. 1011, that's correct. Right? That's what I wanted. It's 11. Yeah. Okay, so now I can take this and mirror it so that it fits in my beautiful 4x7 cage, right? I don't know. Stop. Just make sure I still get 11 out of this. Yeah. So give me this and take it with me here. So this is my actual start point. And where do I, my accept is here, which should be lined up with the start point on this, kind of. The placement of the greens is going to be I need to be a little careful. To make sure that they don't, like, step on each other's feet. And this one has a yellow, by the way. So, ugh. Which one of these is plus? It's this one, right? This one's plus, because it was there before. So... it needs to write only a single green, which will go... at the end of the output. And it's only going to write that at the very beginning, not in the actual loop. So I actually should have replaced that one. And it should actually scan for yellows, not greens. Oh, can I do a yellow-green color swap in here? Would that just fix everything? I haven't had a lot of reasons to do that before, but I think so. Because when it sees... Or, wait, no, I have to be careful. Right, because in the course of adding to a number, I still need 2 spaces on the left of this plus. I need a place for the input and the output, right? And... ooh. So... this yellow... I don't have the input and output properly, like, split, right? That is like before. Here's an example tape, right? I needed to write 2 greens to allow me to have 1 in this area, right? And if I now write several greens, they'll all go kind of to the wrong place. They'll go into the end. And I want some there, but like not that many. Now, I feel like the first time when I did this problem in the original Manufactoria, I probably did the traditional addition algorithm you're taught in school, where you like look at the last 2 digits together. If they're both 1, then you like make them a 0 and carry the 1. If one of them is 1, you make the output value a 1, and don't carry anything. And if they're both 0, you make the output a 0 and don't carry anything. And that seems fine, I guess. But I was so hoping to just use my nice, simple increment and decrement operators. And I think I probably still will. Like, it should be way slower to do it my way. But I assume we have time. Right, because the addition algorithm that you're taught in school is logarithmic in the size of the input, and ours is linear in the size of the largest input. Smallest. Well, the leftmost input, actually. But I could pre-process the tape to get all the markers in place the way I wanted them, right? Scan through the left bit here. Well, write 2 greens, copy everything until the yellow, and then write 2 more greens, basically, I think. And then I could begin. Or write 0 green. Write 2 greens. Write 1 green. Process everything. Write 2 greens here. I don't want to write the second green because that's going to be part of the the loop that we're doing in here is replacing a green that we assume we just read. It would be sort of nice for this top one to use yellow instead of green, though, wouldn't it? So we'd still have that plus in there to indicate like what's being added, and I guess it doesn't matter. Do we have to worry about leading zeros? We were kind of writing them rather haphazardly. I think we still don't. Because well, how do we detect we're done when the input is nothing but zeros, right? And currently our decrementer, when faced with nothing but zeros, I don't even know what it would do. Probably something disastrous. Let's go look at it a bit more close up so I can see it. Well, actually, let's just run the test on it. Give me a 0 or a blue. What happens? I see. We use 2's complement on an arbitrarily large decimal number and just write a zillion 1s. That's not really so great. I mean, it would be really easy just using one scanner. No. Yeah. You could use a scanner right before you enter this subtraction section, which actually, this is the subtraction section, isn't it? To check whether the input, to strip all leading zeros from the input and verify that there's at least a single 1 somewhere, right? And then you would enter the I've seen a 1 recently state instead of the I've seen a 0 recently state. And in that way, you also get your exit condition from the loop, which we needed anyway, right? Which is you have only leading zeros. And then you just remove the plus. And the trailing greens, and then you have your output, your answer in the right area. Okay. So let's kind of work on that, I guess. We wanted to write how many greens? 1 or 2? I think 1. On our way into this guy. Well, we could just leave a well-formed number here. We need 1 green to indicate that the number is well-formed, right? So that it doesn't run into the first guy. So I think we write a green here. Let's spread it out just a little. Well, no, hang on. It's actually got to be further out because we're doing several things. We write a single green. Wait. Isn't that all the setup I have to do? I don't need 2 greens right away. Do I? This guy needs... right. He needs access to the whole tape. Right? In order to reset himself back to the beginning. Because we assumed in our implementation of minus that when we got to the end of our green, the next thing we would be looking at would be our number. So it would be sort of nice if we used like yellow to delimit the end of any number and green to delimit a cursor in the middle of a number currently being computed. Or vice versa, of course, but since we already have a yellow at the end of a number, that seems appropriate. The reason I say this would be nice is then when we are trying to subtract something from this and say, oh, I have to carry, let me go back to the beginning of the tape, I can like read this yellow and then replace it, and then just copy until the next yellow, skipping over the green that's in the middle of the other guy's output, right? And that way, I just need a single yellow divider in between each of the inputs, I think, and a green cursor. But can I put the green cursor there at the right time? Like the initial green cursor. Because by the time I say I want to decrement this number, the problem is I can't put a green cursor in the middle of it because I've got this stupid thing, right? I've got this second number. I got B. Likewise, if I like read to here and then I say, oh, I want to increment this, let me put a green at the end, I can't. Because I've already read through this, and I have A followed by B on my tape. Or B followed by A, I guess. How big are the inputs? Does it tell me? It doesn't tell me. Oh. I guess it tells me enough. Okay, I don't think all this work into the increment and decrement, and I don't think it's possible. Because... because this is a valid... Oops. This is a valid input that I have to produce a solution for. And it would require me to do 2 to the 10th steps, i.e. 1,000 decrements and 1,000 increments when it takes me 400 steps, or about, to do a single decrement. Okay, call it half of that because the numbers won't be all so large. But it's still like 200,000 steps-ish. Okay. So you have to actually implement the grade school algorithm here instead of the functional programming algorithm. Or the mathematician's algorithm, maybe. And a fundamental algorithm. Okay, well, that was kind of 50 minutes spent on not much. I guess I'll just upload that as a video of its own, where we kind of think about Fusion Tender and then realize it won't work. And then tomorrow we'll get to solving it. Hope you guys enjoyed that little diversion. Thanks for watching, and I'll see you next time.